Okay, y'all, this is our worksheet 12, and let's run through that. So for each of the following series, use an appropriate test. Determine if they converge or not. Name the test conditions, all that stuff. So this one here. So the first thing we should do is try to use the divergence test. Divergence test where we take a limit of this general term, and if it limits to anything other than 0, then the series diverges, and that's what's happening. This piece here, let me write it out like this. So for the divergence test, the limit as, it's n. So n goes to infinity of n squared plus 1 over n squared plus 4n. This is equal to 1 because the degrees of the exponents are the same. Degree of the numerator is the same as the degree of the denominator, and the ratio of leading coefficients is 1. 1 over 1 is 1. That's our limit. And then we say, to meet the condition of the divergence test, is that this is not 0, so our series divergence test. That's essentially saying, like if you were to write out the terms, like first term A1, second term A2, plus dot, 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 plus eventually all these terms, you're adding something that's close to 1 every time. And so those, you're just adding 1 forever, and the terms get, or the series gets really big, the sum goes to infinity. Okay, and then this one. So this one's geometric. You have some things to the k. If we rewrote this, we would have 5 over 9 to the k. Geometric series test, size of the ratio is 5/9. Is 5/9, and that's less than 1, so the series converges. Geometric series test. It's not asking for the sum, but just so you see, it would converge to the series converges to the first term of the series, which is 5/9 over 1 minus the ratio. That's 5/9 divided by 9/9 minus 4/9, and that's going to be 5/4. That's what the series adds up to. Connecting that to sequences of partial sums, 5/4 would also equal the limit as n gets, so these are k's, k goes to infinity of the associated sequence of partial sums. Then the next one, okay, that is an alternating series, but it also has this factorial in it. And with the factorial, typically the ratio test is the way to go. So ratio test, that's the limit. K big, absolute, k plus 1th term, 2 to the k plus 1 over k plus 2 factorial times reciprocal of the kth term. And then some things cancel. So limit k to infinity, the -1 pieces, whether they're 1 or -1, as k ranges 0 or 1 to infinity. Those negative ones or positive ones stay 1 because of the bars, absolute value bars. So if we reduce the 2k, this leaves us with a 2 right there. So we're going to have a 2 over, if you reduce k plus 1 factorial with k plus 2, it just leaves us with k plus 2. This limit is 0, and that's less than 1 all the time. So let me think here. So we did the ratio test. The limit we want, it needs to be less than 1 for the series to converge. So converge. This 0 is our R value for our ratio test. It's our limit. If R is less than 1, equal to 1, R bigger 1, the series converges. We're inconclusive. series diverges. Those are the conditions and conclusions of your ratio test. Moving on, second order Taylor polynomial for the approximation centered at 0. Let's see. So this is just a Taylor polynomial. So we have the second order Taylor polynomial. That'll be the series from 0 to 2. And the kth derivative centered at, evaluated at 0, all over k factorial, x minus the center to the k. And since we have a second order Taylor polynomial, we really are going to end up with 3 terms, the 0th, first, and second term. And so 3 terms total, and we need to write out the terms. So we have all of our terms have a fraction. They all have x to the k. And let's see. So let's write it like this. Those are our 3 terms. The exponents are all k. K is 0, k is 1, k is 2. Denominators, 0 factorial, 1 factorial, 2 factorial. The numerators are all the kth derivative evaluated at 0. So we need to find these derivatives. Here we go. So kth derivative, 0th derivative at 0, first derivative at 0, second derivative at 0. So somewhere you need to find these derivatives, and somewhere like off to the side. Let's do that. So the 0th derivative is 1 plus 2x to the negative half. First derivative, negative a half, 1 plus 2x to the negative 3 halves times 2 with the chain rule. Second derivative, 3/4, 1 plus 2x negative 5 halves times 2 times 2. You have this first 2 is that 2, and then this new 2 is the chain rule 2. Then we're going to evaluate 0 into each of these. So if we plug in 0 into here, that's 0, and we get 1 to the negative a half, that's 1. We plug in 0 here, or 0 here. All of our 1 plus 2 x's to the negative what have yous are all 1. So we're going to end up with, this is 1 and this is 1. So negative a half times 2 is negative 1. Then 3/4 times 4 is going to be 3, equals 3. So those are our coefficients. Come back over here, and we would have 1 over 0 factorial, x to the 0. I'm not going to put x in parentheses anymore, minus 1 over 1 factorial, x plus 3 over 2 factorial x squared. And then if you're looking for a pattern, say a Taylor series, then leaving this unsimplified is the way to go because it helps you find a pattern. But we need to simplify this more. Here, 0 factorial equals 1 by definition. X to the 0 is 1. 1 factorial is 1. 2 factorial is 2. So we have 1 minus x plus 3 halves x squared. That's our second degree Taylor polynomial. I guess if you write it in the box or on the line. There we go. Let's use that Taylor polynomial from part A to approximate 1 over root 1 plus 2. Okay, so what we did in the previous problem is say that the function is approximated by p sub 2 of x. P sub 2 of x was the 1 minus x plus 3 halves x squared, and that function's equal to 1 over root 1 plus 2x. All right, so if we want to approximate the function value 1 over root 1.2, then we need to identify what we plug in for x to get a 1.2, inside the root in our function. And so that x has to be 0.1 for this to be 1.2, right? Because 0.1 times 2 would be 0.2, and then plus 1, this is going to be 2, so then 1.2. Yeah, okay, so here x has to be 0.1. That tells us we're going to evaluate at 0.1, 0.1, 0.1, evaluate at 0.1, and our function evaluated at 0.1 is about the same. Oh, and it tells you here what to plug in. Okay, that's your polynomial with a 0.1 into the polynomial. We put a 0.1 here and a 0.1 there. Use the, nope. Use the remainder theorem, Taylor, to estimate. Oh, right. Okay, so this is not the error bound for a alternating series. This is the Taylor error bound. Okay, so the error bound, let's see, the maximum error, the error bound. Okay, so the error bound, let's see. Error bound is m absolute x minus a to the n plus 1 over n plus 1, where m is bigger than or equal to the size. We're going to choose m to be bigger than or equal to the size of the n plus 1's derivative on negative 0.1 to 0.1. All right, so for this context, to find this error bound, you will know or will have been given or have used the x value, the a value, the n value. What has to be chosen is m. So we'll find m in a minute. X was 0.1, a was 0, n was 2, so 2 plus 1. Oh, and that's n plus 1 factorial down there, so 2 plus 1 factorial, and then we need to pick our value for m. To do that, find the next derivative. And by next, I mean, if n is 2, we need the third derivative. And the third derivative, go back up here, third derivative would be third derivative. Let's see. That's going to be negative 15 eighths times 1 plus 2x to the negative 7 halves times 2 cubed. And then let's put that down here. So we have negative 15 eighths, 1 plus 2x, negative 7 halves, 2 cubed. Okay, so the bars make that positive, and we're looking at then 15 times 8. Oh, the 8's cancel, so this 8 and that 8 gone. So 15 over we have equals 15 over 1 plus 2x to the 7 halves. All right, and we're looking at the interval negative 0.1 to 0.1. So this denominator increases over that interval. As x increases from negative 0.1 to 0.1, this denominator also increases. So the denominator here is getting bigger. That means with a fixed number over a denominator that's increasing, the whole fraction gets small, it decreases. And since this fraction decreases on negative 0.1 to 0.1, its maximum value. So let's go back. We want m to be bigger than or equal to this, and that's the size of all the function values of the next derivative on this interval. These are all the function value sizes of the next derivative on this intervals, and the largest function value happens at the left endpoint because we said this was decreasing. If this function is decreasing down into the right, then the max value happens over here at the left endpoint. So m is going to be this evaluated at negative 0.1. So 15 over 1 plus 2 times 0.1, negative 0.1 to the 7 halves. There we go. That is your error bound. All of this. All right. Maybe just another, I guess, illustration on how that works. This size of the function value, we said is decreasing. So on an interval, negative 0.1 to 0.1, whatever the graph looks like, it's decreasing down and to the right. And the function values we're talking about, these function values are these values. And you want the value m to be bigger than or equal to all of those. Now, I don't know, if you look at the y-axis, I don't know what value that is. I don't know what value this is, but I do know this is the highest one. And I want m to be that or larger. And the best possible m is that. The best possible m needs to be bigger than or equal to the third derivative size at negative 0.1. So that's the value we're picking for m. Third derivative at negative 0.1. On the radius interval of convergence, okay, this is ratio test. Limits k to infinity absolute. 2 to the k plus 1 is k plus 2. X minus 1 to the k plus 1 over k plus 1. So that's the k plus 1th term times reciprocal of kth term, k over 2 to the k plus 1 times x minus 1 to the k. And then limit equals limit. And then what reduces away? Here, let's do this. 2 to the k times 2 squared, x minus 1 to the k, and another one. The k plus 1, 2k times 2, x minus 1 to the k. All right. So these x minus 1 to the k's cancel out. The 2 to the k's cancel, reduce. That 2 cancels that one. And we're left with this 2, an x minus 1, and a k plus 1. That's what we're left with. Okay, and the limit only involves the k's. So anything with an x minus or an x goes out front. The 2 can go out front. And then we have limit k to infinity, k over k plus 1. Okay, that limit is 1. So we end up with x minus 1 absolute times 2 times 1. And this is absolute x minus 1 times 2. For the ratio test to imply convergence, your limit, whatever it is, this is our limit. Absolute x minus 1 times 2 needs to be less than 1. So set it less than 1 and solve. So if you divide by 2, absolute x minus 1 less than a half. That means x minus 1 is between negative a half and a half. You're going to add 1 everywhere. So x less than 3 halves, less than 1 half. 1 half. All right, so interval. Oh, we got to check endpoints, don't we? I'm out of room. I'm going to need more room. No, that's not what I wanted to do. There we go. Move that. All right. Okay, so that's your interval right now. The ratio test will always leave you with an open interval, and you have to check the endpoints. So checking endpoints, let's use blue, aqua blue, check endpoints. When X is a half, take your series, plug in a half for X, and then see what happens. We have 1 to infinity, 2 to the K plus 1, times 1/2 minus 1 is negative a half to the K over K. This is 1 infinity 2 to the K. I'm going to do times 2, negative 1 to the K. This K also applies to the 2. So not only to the negative 1 with parentheses like I have, but that K applies to the 2, and it'd be in the denominator. So 2 to the K, and then we have our K. Now these 2 to the Ks go away. And we have the series then. Negative 1 to the K, 2 over K. That's alternating. And so alternating series test, that 2 over K needs to limit to 0 and decrease, and it does. So the series converges at negative a half. And then we come back to our interval over here, and we include now negative a half. Not negative a half, positive a half. That's where we're at. Did I put in I did put in positive a half. All right, then we got to check when X equals 3 halves. Same series, 2 to the K times 2. Let's plug in 3 halves minus 1, 3 halves minus 1 to the K. Three halves minus 1, that's a half. All right, so this would be the same as the other one, except it wouldn't be negative 1 to the K, it would just be 1 to the K. So series 1 infinity 2 to the K times 2, 1 to the K over K and 2 to the K. 2 to the K's go away. All right, so these go away. 1 to the K is 1. We end up with 2 over K. And let's see, this is P series. P series test. P is equal to 1, which is less than or equal to the 1 series diverges. Here's the 1 for your P series. So we exclude the 3 halves, we leave it open. Then our interval, we would write 1/2 to 3 halves open at 3 halves. The distance from 1/2 to 3 halves is 1. And then the radius is half that. You can see that like this. Here's 1/2. Here's 1. Here's 3 halves. There's another way to represent our interval of convergence. That total distance is 1. So the radius of convergence, or R, is half of that, which is 1. Sorry, 1/2. These next ones here, let's move that. Okay, ratio test again. Limit. Is that the same one? 2 to the K plus 1. No, you have K factorial this time. So 2 to the K plus 2 x minus 1, k plus 1 over k plus 1 factorial times k factorial over 2 to the k plus 1, x minus 1 to the k. We should be left with limit k to big absolute, a 2 again up there, an x minus 1 up there, and then over k plus 1. K factorial. So again, 2k's go away, a 2 there, cancels that one. You're left with 2 to the 1. X minus 1 to the k's go away. We're left with a single x minus 1. K factorial, k plus 1 factorial gives you k plus 1. All right, that limit is 0. And as we're here, let's write it like this, equals 2 absolute x minus 1, just like last time. And then limit, though, k to big 1 over k plus 1. This piece, this goes to 0 and then multiplies times this thing, which makes it 0 all the time, regardless of what x was. So if you want to see that a little different, okay, so we have our limit being 2 times absolute x minus 1 times 0. That's 0. It's less than 1 for all x. For all x. X could have been anything right here. Subtract 1, absolute value times 2 times 0. You're going to get 0 every time. So all x is your interval. Half of that for the radius is a half. This last one is your going to give you an example of your third possibility for a interval of convergence. Let's see. Okay, so ratio test again, limit k to big, absolute, k plus 1 factorial, x minus 1, k plus 1 over 2k plus 2 times 2 to the k plus 1 over 3 factorial, x minus 1 to the k, and we end up with limit k to big. The factorials give us a k plus 1 in the numerator. We're going to have an x minus 1 in the numerator, and we're going to have a 2 in the denominator. Okay, so let's see. We would have then absolute x minus 1 over 2 times limit k to big of k plus 1. This limit here goes to infinity. So that goes to infinity. Let's make this small again. So then our limit we would have equals absolute x minus 1 over 2 times infinite. This is infinite. And we want to know, is it less than 1? And you kind of have to look back at your limit, or you have to look back at the x, or look back here. Because we took our limit, we had this thing in front, but then we had infinity. So you're kind of thinking no matter what this is, we're going to hit it with a big thing, infinity, and we're going to get infinite, which is never less than 1. So it's like we tend to think, no interval of convergence, but that's not true. At this point, if you get infinity for your limit with a ratio test, then this tells us there's going to be a single value for our interval, and it's the center. It's, is there a value for x that would make this 0, such that 0 times infinity would give us 0, which would be less than 1. And that happens when x is 1, or the center. You can look back here. If x were equal to 1, then this would be 0, and we'd have a bunch of zeros, and that series would converge to 0. So our interval of convergence is the single value 1. And if you look at that on a number line, here's 1. That's 0. Here's 1. That's our interval, which means there's no length to it. And so our radius is nothing. Okay, I know that took some time, but hopefully that's helpful to hear how, I might talk through that. Y'all take care. See you. Well, I won't see you. So great. Yeah, good luck on your semester. Sorry, good luck on your final. and reach out with any questions. All right.